My name is Baptiste Mazurié, and so I'm here to present you various applications of data reconciliation at EDF. So, well, a few words about EDF. So it's the French leading electricity company which operates nuclear power plants. But here the application mentioned today are, well, typical experimental application. So that everyone here can relate to them. So first, well, what is data reconciliation and why am I talking about this here? Well, I'm using the data reconciliation implementation from OpenModelica, hence my presence here. So regarding data reconciliation, what is it? So it can be described as a method to ensure a better state estimation of your system by binding the equation of your system and your measurements, so that they are coherent with each other. But, well, I'll get back to what is data reconciliation more theoretically in the first part of my presentation, and then we'll follow up with two different applications. First, an application of detection of defects, and then on the validation of measurements. So first, well, what is data reconciliation? So as I've mentioned, it's a method to correct measurements and using, well, an optimization problem under constraints. And so you are using the physical laws of your system. So for instance, conservation of mass, of energy, so that your measurements are coherent with each other. So the goal is to improve the system state estimation, as I've mentioned. And because you have a better state estimation, maybe you can use this method to, well, first detect failure, for instance, or also, well, to improve your measurements, because you will have, in the end, a better uncertainty on those measurements. To run data reconciliation, well, we need some assumptions regarding well, what we have. First, we need redundant measurements, and we also need the uncertainties regarding those measurements. And also, well, we need a model, so a behavioral model. It will describe how the measurements are linked to each other in a way. Regarding the data reconciliation implementation in OpenModelica, it has been done regarding a norm, a German norm named VDI 2048. And because of this norm, well, we have some additional assumption regarding the Gaussian distribution that the measurements should follow. So a measurement is described as a Gaussian distribution, and the model is in a steady state. So, well, how to do data reconciliation? First, well, you need, as I mentioned, redundant measurements, so X, and the corresponding uncertainties, so sigma. So those measurements, well, can be pressure, temperature, mass flow rates, for instance. You also need, well, a model to represent and to bind those measurements together. If I stick to, well, and it will be described as f of x is equal to 0. And if I stick to an example, for instance, a fluid splitter, so pipe dividing in two other pipes. So for instance, here, well, the equation behind it, if I stick to the mass flow rate, it's, well, quite easy. It's the conservation of mass between the flow rates in the different pipes, for instance. What are the outputs of data reconciliation? Well, when you run data reconciliation, in the end, you have, well, physically consistent measurements. So you have your reconciled measurements, x hat, which are physically consistent, so it respects the equation that you mentioned at the beginning. And also, well, those measurements will be improved. Well, improved in two ways. First, it will be closer to the true states of your system, hence a better state estimation. And also, well, improve because you will have a reduced uncertainties because of the method used. So, well, in the end, you have a better understanding of your system. How to use it in OpenModelica? Well, it's quite straightforward. For the measurements and the incentives, it's given as a CSV. And for the physical model, well, it's the strength of the implementation in OpenModelica. You use, well, a Modelica model. So either, well, you directly code your equation, or you can also reuse a model already implemented. Then you use the OpenModelica feature, which is embedded in the standard release of OpenModelica. And then you have your results. So you have the initial measurement that you gave, and then the intensity value. Same for the incentives. But well, how to know if maybe those measurements that you gave just before at the end, those results, can you always trust those results? Well, not always. If the results are, well, too different from the initial measurement that you gave, maybe something is off. And well, that's why different statistical tests have been implemented. So first, a global test setting if the measurements are, well, consistent with the model. And then a set of local tests. So for each measurement, is the recurrency value, well, not too far from the initial value? And if it's the case, well, maybe there's a default or there's a local failure and it should be investigated in a way. So now that I've explained in theory what data reconciliation is about, well, first case study. So it's hydraulic test loop at EDF. It's made for, well, testing different sensors regarding water flows mainly. And so it's something which is at industrial scale. And well, it has, well, some very good sensors. So we have a precise idea of what is really happening in this system. And so, well, maybe we will try to use data reconciliation because we have redundant measurements. And because of the modularity of the system, we can add defects in the system. What do I mean? Well, you can replace, for instance, a pipe with defects. So for instance, well, maybe a step, maybe well, a step defect or well-bit defects, which would impact the flow. And because data reconciliation gives you a better state estimation of your system, well, can data reconciliation detect such defects? It is a question. So, well, to run data reconciliation, we need measurements. So we have the test loop, okay? And we also need a model. So a model of the test loop is implemented using a ThermoSysPro library. So it's an open source thermohydraulic library developed at EDF. And then, well, we run data reconciliation on a test campaign. And well, if we run with the normal model and the measurements with the defects, well, we see that the local and global tests are false. It means, well, something is off, and so there is a defect and you should investigate the result. But the question is, well, how effectively can it detect such defects? So for each test campaign, we will compute the local tests, compare it to a threshold. And so if a test with a defect is detected with a defect, it will be a true positive, and so on. So for each 105 measurement sets, it will be computed. So as I've mentioned, if a test has a defect and is detected with a defect with data reconciliation, well, it's a true positive. If it has no defect, detected with no defect, true negative. And so if, in a way, well, a test with no defect is detected with a defect, it means it's a false alarm. So it means the data reconciliation will tell you, well, something is wrong, but in fact, well, not really. So that's why we want as few as false alarm as possible to see the, well, effectiveness of the method. Well, we can compute sensitivity and specificity And those two numbers should be equal to 1 to have a perfect diagnostic. It means you have detected all your defects and you have no false alarms. So let's try it on a test campaign and see, well, what we can see. So for instance, for the step defect, which has the greater impact on the process, should be detected. So if we compute sensitivity and specificity for every test campaign, and if we compare to the default threshold of 1.96, well, we see that indeed we have a perfect diagnosis because sensitivity and specificity are equal to 1. But well, one can wonder, is there always a perfect diagnostic? If we take another test campaign, another defect, well, we see that still there is a perfect diagnosis, but with the standard threshold of 1.96, we would only detect like 35% of the defects. So with the current instrumentation on the test loop, we would only detect those 35% of the defects. So with this fixed instrumentation. So we see that with a fixed instrumentation, we have, well, great impact of the threshold lambda and the diagnosis. And then finally, for the last defect, which is the one with the less impact on the flow, it's quite hard to detect it with the current instrumentation on the test loop. So that's why we would need a more precise instrumentation to detect such defects. Well, now I'd like to talk about the second study case. It's regarding the validation of measurements using data reconciliation. By the way, the old name of data reconciliation is data validation and reconciliation, DVR. So, well, it's here in this case, it's really for the validation of measurements. Another test loop, this time using air instead of water. So we need to provide air at different stations, and air is taken from the outside and may need to be cooled down first on hot days. So you need a certain temperature and also maybe to reduce humidity, for instance. Well, because it's because of humidity, condensation may occur, which makes the phenomenon quite complex, and thus we need to model this model. And hence the model is developed. The question occurs, well, how to calibrate this model? There are plenty of calibration algorithms, so that in the end you have a calibrated model. So what do you need? Well, first a model to calibrate, okay. And also, well, it has been mentioned today, for instance, in the keynote, well, you need also data. It's very important. But more precisely, when you have data, you need good input data, hence the validation of your measurements. This point regarding the importance given to the measurements is key. Nowadays, okay, data are important, but you need data which are really usable. So the quality of the data that you have is really important. And it's not only the case for calibration, but for all applications having experimental measurements in a way. I've wrote it here again, but it's really important. And hence the use of data reconciliation. So it offers a method to improve the reliability of your measurement, to improve those uncertainties so that you have a better state estimation. Let's apply it to the heat exchanger I've mentioned for the air. So we have an airflow that we want to cool down. So it will be done thanks to a water flow. And because condensation may occur, we will have a condensation flow rate in the end. For that reconciliation, we did a model. And here first, well, quite simple model will do the trick so that we have coherent measurements in the end. So just to compute the power from the inlets and outlets of the different flows. What can we measure? Well, temperature, flow rates, humidity mainly. So we run a different measurement campaign on those variables. And so in the end, we have 15 test campaigns. In the two next slides, so I will take two different test campaigns. One where we validated the results and it's coherent, and one where data reconciliation helps you to, well, maybe discard or maybe say something is wrong about those measurements, because it's quite hard to measure such a system. So in the first case, we want to compare, well, the initial measurement that you gave, which has a Gaussian distribution, and the reconciled value, which also is Gaussian. So we will compare it using, well, Python and OpenModelica library, which is also an open source library developed at EDF with Airbus and FIMECA. And well, we see that it's coherent in a way. The distribution are not too far from the initial measurements. And we see that the accuracy, for instance, for this measurement has been improved. So those distribution prior and reconciled are consistent, and those measurements could be used, for instance, to calibrate a model after. If we take a second test campaign, well, in this case, we see that the reconciled value are, well, maybe too far from the initial measurement that you gave, for instance, here, with cross. So you would have local test wrong, for instance, on this test campaign. Well, so those are inconsistent, and thus, well, you should have a better analysis on those measurements and say, well, what is wrong? So in the end, for EDF, this test campaign has been discarded regarding the analysis. Just a point regarding the conclusion of data reconciliation. Data reconciliation does not tell you which sensor is faulty in the process. It tells you something is off, and you should investigate the reason. For instance, here, maybe we could think it's this sensor, but in the end, it's not. So it tells you something is wrong, but you should have a better analysis on the reason. In conclusion, so on the two applications, well, for the first one regarding detection of defects, so it's detected the defects in a way. We see that the impact of the threshold lambda is quite important at a given instrumentation setup. And regarding the application on the heat exchanger, well, it's gives us test campaigns that could be used for calibration, and we discarded two different test campaigns. Regarding the perspective, well, the current implementation of data reconciliation in OpenModelica is technically still a prototype, but we've seen here another application using industrial data, and which can be used, so it's a good point. Maybe, well, okay, work needs to be continued, well, for instance, regarding documentation or pre- and post-processing, but in the end, it's usable for industrial usage. And also, well, for instance, we need to conduct more work regarding the scalability of data reconciliation in OpenModelica on more complex models. Thank you very much.